So True Circuits, we've been in the IP business since 1998. That makes us one of the oldest IP and really one of the oldest, certainly one of the oldest hard IP. So we build analog mixed signal IP. Our history is in clocking, timing IP, PLLs and DLLs, things that provide the heartbeat for the chip. We're in Los Altos. What makes us different is obviously we have an expert team. Our president is one of the leading experts about PLLs and wrote some of the seminal papers. But also we have a very automated, and we use a lot of our own proprietary tools. So at the foundation of everything we've done over the last 15 years is a very powerful characterization platform, a lot of automated placement, things that can do a tremendous amount of productivity and efficiency is gained out of that. And what we've done is we've taken this basis, this way we've done smaller pieces of IP, and we've applied it to DDR, which is a much larger problem, but is based in timing, and we've thrown our entire timing portfolio, our entire arsenal of IP at that problem. But it also requires sort of a different way of approaching it. So we're able to put all of the data into one database. If you were to come into our company and you looked at our PLL design, it would look more like soft IP than hard IP. It wouldn't be schematics, it wouldn't be things like that. Everything is embodied in one database. That database can do SPICE, it can build gate level, it has placement information, and that's one of the critical things for DDR. Most people, probably all people, now have to approach the DDR problem as a custom layout problem, because you're running 32, 64, 72 bits, you're running it up to 3.2 gig, all kinds of matching and delays. So if you approach it as a as a custom analog job, it's going to take a lot of people a long time to build it. And once you build it, you're not going to want to change it. Now, juxtaposed against that is the fact that DDR has a big impact on the cost of your chip. And it's really hard to have one size fits all. Depending on what business you're in, you might want a DDR5 that looks one way. You might want a flip chip with 4 or 5 deep pads, but that may mean that the package and board cost is really high. Your next chip might be a high volume chip for digital TV. Suddenly, you want to put it in a different package, and suddenly cost is really key. 25 or 50 cents of packaging cost might be the difference between choosing to be in the business or not. So what we've done is we've brought our analog mixed signal platform so we can get the best of both worlds. We can build a PHY with tremendous amount of physical flexibility, so it looks like you've decided exactly the I/O ring you want, the bump array. We build a hard macro that's totally timing closed that fits that. It looks like it's custom, but behind it, it's configured, much like soft IP. Oh, you're there. Where are we? What? Let's do this. That's fine. This is perfect. No, go where you were was fine. Let's do the picture. So I'll talk about DDR. There was a couple more slides about our existing portfolio of PLLs and, spread spectrum, infractional, things like that. But you guys can see that on our website or on our booth. So if you look at this DDR5, I've talked a lot about the physical flexibility. Other features are, the tricky part of DDR is it's a parallel interface. So it could be very wide, and the data needs to arrive at the same time. So all the different, skews between the bits is really important. We built a PHY where every bit looks more like a SerDes than it does a DDR controller. So every bit of the DDR PHY will adjust to the data. It will sample the switch point of the data, and it will automatically and continuously adjust. So, bits that are next to each other will automatically deskew. They could be off by maybe plus or minus half of the UI, no problem. So that's good. A lot of the effort in the package and board is matching all these trace links. So, you're taking 400 or 500 pins through your package that you're trying to keep as cheap as possible out to your board. You're trying to match all the links. You're trying to keep all the ground and the return paths the same. It's really tricky, and it can be expensive. You can always solve a problem by putting another layer on the board and another layer in the package, but that's a really expensive way to go. So you don't have to worry about that matching. That goes away. We're adjusting continuously, so our belief is a couple of things as we go to these higher speeds, that you need to do a lot more tuning and training. So, in the old days of DDR, you might just tune it once per board, maybe once on a cold start, but your data eye and your margins at these speeds are so small, we want to adjust all the time. So all our read stuff is continuously adjusted. We place a strobe separately for even and odd data, and we keep it in the center, and it's continuously there. We've also added some resources to do write training without having to completely take your processor down or get completely out of band. So all that can be done automatically. There's also in DDR4, you have to adjust the V-references on your PHY and also in the DRAMs. All that's done automatically. Most of our customers are spending more money on the software than the hardware. So anything we can do that reduces the drivers. So instead of our customer having to spend 6-man months writing drivers to tune it, all that's done automatically. So one other thing, if you have a wide PHY, it could go around maybe 2 sides of the chip, maybe even 3 sides, so things are going to be far away from each other. We've built every byte slice to be basically source synchronous. So you can have the central part of your PHY here. You can have one of your byte lanes all the way across the chip. You could theoretically have it on another chip. We take care of all that. And then we also, no matter how wide your PHY is, we bring all the data together and we pass it along a narrow interface to the memory controller. And we also use some of our timing IP to deskew the clock so that the clock uncertainty between the DRAM and the PHY is very low. This allows you to easily synthesize and close timing on your memory controller. It might even allow your memory controller to run faster. Maybe you can run it at a 2-to-1 ratio instead of a 4-to-1 ratio. And closing timing on the soft IP side is one of the really big problems. And so this keeps that simple and allows you to do it. A lot of times you're going to be doing that late in the chip, so it might be one of the last things that you're closing timing on. So, those extra weeks that it takes are under a lot of scrutiny because you're probably already past your tape out date. So I talked a lot about the flexibility. A couple other things, we added some, we took advantage of resources that were already in the chip. So with a very small increase in the gate count and size, we've added some interesting instrumentation functions. So while the chip is running, you can actually get information about, let's say, jitter. You can get you can pick some points on the distribution. You can look at the 1 or 2 sigma point. In a register, you can see, this particular pin has a lot of jitter. Maybe it has a impedance mismatch somewhere along the way. You can very quickly identify weak pins. You can actually, with firmware, you can completely map the data eye. So without a scope, with just a computer or a laptop, you can completely map the data eye. You can look at the jitter. There's actually a feature where you can launch a TDR pulse, and you can measure the flight time, and you can even look for fairly gross reflections, impedance mismatches. So the idea behind that is when your chip comes out, until the memory interface is up, there's not very much you can do with the chip. So it's crucial to be able to bring the memory interface up quickly, identify any weaknesses, make any patches that you might need to make on the board, so everybody else can get along with their, evaluation. And if that memory interface is delayed by a week, that's probably a week right in the critical path of everything. It means your whole project is probably going to slip a week. So we've added a lot of things that allow you to do that. Our memory partner, initial memory controller partner for this is Northwest Logic. It's just PHY's DFI compatible. It can work with anybody. But we did some things with those guys. We built we built on a standard so that we could do a lot of this automatic stuff we're talking about very easily and very cheaply. They also have a small module that creates memory test patterns. So what you can do if you were to use us in Northwest Logic and buy this little module, you can completely bring up the memory interface without even having to talk to the rest of the SoC. You could go in through an I2C pin or maybe a JTAG pin. You could launch all the interesting data patterns. You can use all the instrumentation inside the PHY. With just a laptop, you could map the data eye, you could look at jitter. I mean, you can really do a whole lot of work, and even if the rest of the chip has problems or CPU doesn't boot up, you can still bring the memory interface up. So that's another good thing. You don't have to do as many things in sequence. And in order to do that, you use a lot of these instrumentation features that we've added. Let's go again. Okay. Obviously, you have to test it, so we have some of the standard boundary scan and things like that. But one of the most interesting things is we have a really powerful loopback. And it's really more than just loopback. We're actually sending data fully out of the write path and bringing data back into the read path. It could be looped around the same pin, before the I/O, after the I/O, or it could be externally looped to another pin somewhere else in another byte lane. So that allows you to completely test read and write at full speed without an expensive tester. It means that some of the DFT logic that might slow down the critical path doesn't need to be there because you're testing it as it's actually being used. So that's important. It also tunes itself too, because a lot of times for this loop back, the test engineers trying to figure out, okay, I need to wait another cycle or come up cycle early. They spend a lot of time tuning it. Maybe that tuning changes between lots or over temperature. So it can make the test job kind of tricky. And what we do is, since we're sending things out the write and back into the read path, we automatically train it. So none of that's necessary. If it changes from lot to lot or over temperature, that's not a problem. So, basically what we've tried to do in a lot of these things is make it easy and fast.